Welcome to our tutorial sessions in the run-up to ESORICS 2021. Professor Avishai Wool from Tel Aviv University will talk about securing legacy communication buses. Avishai Wool is a professor in the School of Electrical Engineering at Tel Aviv University and Deputy Director of the Interdisciplinary Cyber Research Center. He has published more than 120 research papers and holds 15 US patents. He advised 5 PhD and 40 master students and has served on the program committee of the leading IEEE and ACM conferences on computer and network security. We are surrounded by cars, airplanes, and power stations that run perfectly well in their internal networks, which were designed before anyone dreamed of connecting them to anything outside like the internet. But then they got connected to the Internet of Things, offer dangerous attack surfaces, and reveal terrible vulnerabilities. Professor Avishai Wool explains how anomalies can be detected and intrusions be prevented in legacy systems. Please write your questions in the chat. He'll read them and answer them. Professor.
Thank you very much, Georg. Let me share my screen. And okay, I hope you can see my, can you see my screen?
Yes, I can.
Well, at least I have one person in the audience. That's great. Thank you, Georg, and welcome everybody. I'm Professor Avishai Wool, and today we're going to talk about securing legacy communication buses and industrial control systems in vehicle and in aircraft networks. And like Georg said, feel free to ask questions over the chat. I have it open and I'll try to answer as best as I can. So let's jump in. I have a lot of material to cover, so let's just get to it. So I'll start with a very brief history. So networking systems that we're going to be talking about today were designed a long time ago in the previous millennium, something like 40, 50 years ago. And I'm going to focus on 3 types of systems. They have things in common, but they're different. So we'll talk about industrial control systems, or ICS for short, and we'll take a look at the leading protocols in those environments, so Modbus and Siemens. Then we'll talk a bit about cars, about what's under the hood, called the CAN bus. And we'll talk a bit about airborne systems with the ARINC 428, 429 networks. All of these systems, each in their own domain, was designed under the assumption that it's isolated. So the engineers that developed these thought of something that was, far away from other networks. It was just doing its own thing. Anything that was connected to the network was generally legitimate. So the adversary they had in mind was nature. It was things like noise and interference and radiation and so on. Nothing malicious. They didn't imagine any kind of malicious activities. And these are very successful networks. They are very common. They're in high-profile systems like power plants and cars and airplanes. They are important, but they have no defenses against any kind of malicious adversaries. Okay, fast forward 40 years into the future, these networks are no longer isolated. They are connected to all kinds of other things. Sometimes they have wireless elements. Sometimes they have real internet connectivity. They use components off the shelf. They use standard protocols encapsulating them. So the result is basically headline making attacks. You may have seen these in the media. I'll show some examples later. This is where we are. And these networks have what I'd like to call the curse of success. They were very successful. They're good technologies. They're ubiquitous. They're everywhere. And now we find that they are deficient and have problems, and we want to fix them. And it's difficult. It's difficult, it's slow, it's expensive, because these types of environments are built to last. They're not cell phones. You don't replace them every 3 years. Power plants expected to work 50 years. Cars are actually required by law in some countries to continue to function, and manufacturers are supposed to continue manufacturing spare parts for 25 years by law. Aircrafts are also very old. The aircrafts that you fly in, many of them are, decades old. They're expensive machines and they keep running. So replacing things is difficult, it's expensive. And while all of these networks have modern replacements that are much better in security, we still have a very interesting question of, okay, what do we do in the interim? And the interim could be decades. So it's important to secure these legacy networks. And then we have a question of how do we retrofit security into these existing systems? They have limitations. Where do we stick the new stuff? It's not easy to do. So what can we do? Well, usually the easiest thing to deploy is an intrusion or anomaly detection system, which is passive. So deploying passive things is not so threatening, and that is very common, very often something that you can do with minimal impact. Sometimes if you're ingenious enough, it's possible to also deploy intrusion prevention systems. So you can introduce active things that defend these network systems internally. Sometimes you can update rather than replace protocols. You can update parts, you can add things to them. Not always possible, but sometimes it's possible. So what I'd like to do is really survey this environment and show you some of the things that that we've done in my lab with some of my students and collaborators. So I'll start with a survey of these three areas that we're talking about. We'll give you some color on what they are. So industrial control networks, and specifically Modbus and Siemens, and we'll get to CAN bus for cars and to ARINC for airplanes. So I'll share with you a little bit about how these networks and protocols function. And then we'll turn around and go over the same material again, but this time look at potential defenses that we've suggested and how well they function, and you'll get some kind of idea of the types of problems that we encounter. And hopefully maybe you'll find ideas for you to do some research as well. So let's begin. Let's talk about industrial control networks. So here's a typical example of a power plant. This is a photo of a coal burning plant next to the Mediterranean in Israel. So on the left is what it looks like, or what it looked like a few years ago. And on the right-hand side, you see roughly what is inside. So there's various types of machinery. There's a boiler and turbines and steam and transmission lines and many other things that generate electricity. And if we think about, okay, what's going on inside? So first of all, there's a lot of control theory, right? You have machines moving and they're generating things, and you need to control them to make sure that the power output is correct. And so there's lots of control theory and differential equations and so forth. That's all in there. That stuff is implemented on what are known as programmable logic controllers, or PLCs. These are basically little computers, specialized computers, that run this type of control logic and affect things around them. They open and close valves and start and stop engines and so forth. So they're little specialized computers. Remember the name PLC, it's going to be a star of today's presentation. These controllers, there's not one of them, there's many of them, and they're all connected to a network. And this network has all these sensors and actuators. These are the PLCs and what they control. There's also a control room where you have a person looking at big screens and checking that all the industrial processes are functioning correctly. So there's a human machine interface, some kind of UI that shows the person what's going on with the system. And all of these sensors and actuators are actually controlling the water flow and the coal burning and the temperature and the output power and so forth. Now, this network here in blue, this control network, is running the protocols that I'm going to be talking about. It's running these Modbus or Siemens S7 protocols, which, as I said earlier, are completely insecure. There's no defense there at all, which means that anybody that has access to this control network, they can somehow connect to it. Potentially, they can own all the PLCs. They can send them commands. They can read stuff from them. They can write things to them. They can shut them down. They have generally full control, which means that they can do a lot of damage if they have this access, because the protocols do not protect themselves in any way. Now let's take a little bit more look into the PLCs. So as I said, these are the core of the industrial control systems. They are connected to sensors and actuators. They run the control program. So they're the bridge between the cyber, the virtual computerized world, and the physical, the kinetic world. So they actually cause things to happen in the real world, things that potentially could go boom. And they have this is like a user interface that controls the PLC. So this is what this is a photo of a Siemens PLC. It has some minimal UI locally, and actually each one of these vertical bars is a PLC on its own. And there's a control system. This is probably a view of the engineering system that configures these. Okay, so I said there have been attacks against these systems. So the mother of all cyber attacks against industrial control systems was the Stuxnet worm 11 years ago that harmed uranium enrichment turbines in Iran. That was, created a lot of noise, and we'll say a few words about that soon. But it hasn't stopped then. In 2015, there was a pretty famous attack on the Ukrainian critical infrastructure, basically causing power outages for a few days during a war between Ukraine and Russia. So this was an act of cyber warfare. And this is ongoing. Just last year, there were attacks against Israelis' water system, trying to shut down water supplies. This was attributed to Iran. So these things are happening. It's part of modern warfare, and I think it's going to continue and escalate even further. Okay, so what can the attacker do? Suppose you're an attacker and you connect to this network. What would you like to do? What could you do? So there's a number of things that you could do. For instance, you could cheat the sensors. If you can feed the PLC wrong sensor inputs, it will affect the control system, and then the control will do some weird things. So if, for instance, you can control the temperature and cause the PLC to think that the temperature is now 0, then it will kick into some kind of heating mode and will increase the temperature beyond what it should. You could also set long-term goals that are incorrect. You could tell the system, stabilize on this new control target. Let's say, send it a command saying, set the heat to 1,000 degrees centigrade, and the PLC will just do what it can to make the temperature reach that goal, which probably is too high. Or you could just erase the control logic completely if you can. If you have the access, you can actually replace the control program so that it doesn't run the differential equations that it should. Instead, it just does something adversarial, just let's say turn the heaters on regardless of any in-sensor input. And while you're at it, you can show the operator some kind of message saying that everything is fine. This is roughly what Stuxnet did. They basically turned on the turbines to excessive or incorrect speeds while showing the operators that everything was functioning nicely. Okay, the result of all these things, as we saw before, affect the world we live in. So something could actually go boom and cause damage. Okay, so that was our brief introduction to control systems. Now let's switch gears and talk about cars for a second. Okay, so what's going on with cars? So let me start with, a definition. Okay, what is a car? Okay, what's a car? And so I went to Wikipedia and I copied the definition of a car, and it says, rational things about vehicles and how many people can be in it, and so on. It drives on roads, etc. Okay, so that's all great. My definition is a little bit different. I define a car as a computer network on wheels. Okay, it happens to take people from place to place. that's a side effect. It's really a computer system. It's a computer network. If you don't believe me, computers are everywhere in the car. They're not called computers. They're typically called electronic control units, or ECU. So instead of PLCs that we saw in industrial networks, in cars, they're called ECUs. It's the same thing. It's a tiny little computer that's specialized to do the tasks that it needs to do. And it's usually rugged and against vibration and oil and other things that happen inside the car. Old vehicles had just a few of them, like for the engine control, for the radio, and they were totally separate from the outside world, and they didn't have any kind of communication outside. That's like way wrong now. In modern cars, does anybody want to guess how many computers exist in a modern car? You can write it in the chat. Just type a number. How many computers you think are in a modern car? Take a guess. Okay, I'm seeing guesses. Roland is saying 30. I get Shayras going up to 100. Harold went all the way to 500. Okay, you're in the right neighborhood. So, an old style car has roughly, 30 plus ECUs in it. An electric car has upwards of 100. I don't know if Harold is just over guessing, or maybe he knows something that I don't, but 500 seems a little high to me, but it could be the trend is clear. So these are big numbers any way you look at it. And so what do? They do all kinds of things. They control various aspects of what the car does, and they're all connected to each other using what is known as a controller area network bus, or CAN bus for short. It's a networking technology that was designed by Bosch over 40 years ago. Some of these ECUs actually do connect to the outside world in various ways. So, clearly the radio, but also Bluetooth, internet connectivity. There's the emergency button. There's load jack. There's upcoming vehicle to vehicle and vehicle to road connections. There's internet access in the car. There's lots of communication paths into and out of the car. And people have noticed, and we've seen some published hacks. This is a photo from a very famous attack about 6 years ago by Miller and Valashek, where they actually, from remote access, they took over control of this Jeep and took over the steering and drove it off the road into the ditch. And there have been other examples. It's not just Jeep, it's other vendors as well. That this particular attack, it wasn't even an attack, it was just a demonstration, friendly demonstration. It caused the recall of 1.5 million vehicles, and there have been more. This is not the last one. So if you're interested, you can find videos and watch them. It's pretty illuminating to watch. A few words about the CAN bus protocol itself. So just to give you a clue of how challenging it is to secure such a thing. So CAN is a real-time protocol that has very, very short messages. 8 characters is a full message of CAN. Okay, 64 bits, that's it. Each message has an ID. It's an 11-bit ID. Every ECU, quote unquote, owns certain message IDs. It is the only ECU that is supposed to send its own IDs. And the messages are broadcast periodically. So there's no destination. The messages are just sent like a TV station. Each ECU says something and repeats it a few times. And all the other ECUs that are listening, if they're interested in whatever that ECU said, then they take action. So if you look at the network, you don't know who's talking to whom, because everybody's talking, every ECU is talking to everybody at once, and you don't know who's listening. Okay, so you can wrap your mind around this kind of style for a second. So here's an example of how this kind of communication works. So imagine this is, some of the numbers here are fake, but the rest is real. So suppose you have the gear handle and there's a gear handle ECU, which has a message ID of 157, and basically it transmits some code that says the handle is in the D position, it's D in the D, handle is at D, at D, at D. It repeats the same thing, saying broadcasting the position of the gear handle. While this is happening, the gearbox has its own ECU, and the gearbox ECU is transmitting its own status. It says, I'm in neutral, I'm in drive 1, I'm in drive 1, I'm in drive 2, I'm in drive 2. It's just saying what its position is. And while all of this is happening, the dashboard ECU, listening to all these broadcasts, puts the letter D on the driver display so the driver knows what's happening. And what the dashboard is showing could be either what the gearbox is actually doing or what the gear handle is trying to do. And I don't know to tell you which one it is. But that's roughly the style. Okay. Now, what's the adversary model in the CAN bus network? So really, the adversary model is a spoofing attack. So typically, what happens, and this is exactly what happened in the Miller-Valashek attack and in the others, the attackers somehow compromise some ECU, like the infotainment system, the fancy radios, and there's a big computer there, and it has internet connectivity or wireless connectivity or something. They take over one of these ECUs, and then this ECU can send a message. It could broadcast message with some kind of ID A, and even though it's the infotainment system, there's nothing stopping it from broadcasting message that effectively says, I'm the ABS system, the car is unstable, the car is unstable, the car is unstable. And as a result, the engine ECU maybe will stop the car. Okay, this and the ABS system, the real ABS system, is not doing anything here because the car is perfectly stable. But the message is broadcast and the engine doesn't know who sent it. It just sees IDA, and IDA means ABS, so it does what it does. Okay, so this is the style of attacks on CAN. And you can already see that because the protocol is so primitive, it's going to be pretty difficult to secure. All right, let's switch gears and talk about airplanes for a while. So aircraft also has computers on board, lots of computers, lots of cables, miles and miles of cables inside an aircraft. And the leading protocol and network design is used based on ARINC 429 for civilian aircraft. The military have their own, and it's different. But civilian aircraft use ARINC 429. It's a standard. And it is the most common bus protocol in the avionics industry. Again, it was designed over 40 years ago, has no security features whatsoever, doesn't even have source authentication, so you don't know anything about who's communicating. And as you can imagine, it's important. So so far, cyber attacks on aircraft have not made the news, luckily, because if that would happen, we would see aircraft falling out of the sky, and that's kind of unpleasant. But that doesn't mean it cannot happen. There's not a lot stopping it from happening. Just so that we have terminology, in ARINC terminology, these elements on the network are called line replaceable units, or LRU for short. So in cars, we have ECUs. In industrial networks, we have PLCs, lots of acronyms. In aircraft, we have LRUs for some reason. That's what they're called. And one surprising aspect of the ARINC networks is that on a single bus, so a single network, you're only allowed to have a single transmitting LRU. Just one LRU transmits, and you can have up to 20 receivers listening to that one LRU. So the communication is entirely unidirectional from the transmitting LRU to the others. And this unidirectionality is enforced by the wiring. So a receiving LRU is physically unable to transmit back on the same bus because its transmit and receive cable inputs are set up in a way that it can only listen, it cannot transmit back. So if you want to have bidirectional communication, you just lay another cable, and there's another bus going the other way, so that let's say this LRU on the right-hand side is able to talk back to the transmitting LRU on the left-hand side. So there's going to be another physical cable, which sort of explains why I said that there's miles and miles of cabling in the aircraft, because all of these cables are unidirectional, and if you need bidirectional, you need two cables, and these are thick, heavy cables, and it's a mess inside the aircraft. So what's the threat model that I want to present to you in this case? So there are other threat models possible, but I want to stress a particular threat model that we looked at. That's a technician attack. Okay, so we're not thinking about a situation where an attacker, an adversary, let's say, takes over one of these LRUs and injects fake logic or adversarial logic into it. We're talking about a technician attack where, while the aircraft is on the ground, a malicious technician with access opens up the belly of the aircraft and does something physical. So either they replace the transmitter and put a different transmitter there, a modified transmitter there, or they physically replace one of these receivers, or they add an extra receiver to do their malicious goals. So we're actually talking about a hardware swap. And so this is a slightly different attack model that we've mentioned before. It's also interesting for its own reasons, and a technician has lots of power, and it's something also to consider. And I wanted to bring it to your attention as another type of adversary that we might want to worry about. So in this environment, what can you do? Here, what is possible is to deploy an anomaly detection system. For instance, you could deploy something, an extra legitimate system that listens on the bus and checks whether all the communicating parties on the bus are legitimate, or if there's a new one that seems suspicious. And this can be done, as I'll show you later on, using hardware fingerprinting. So you can do this basically identifying the hardware that is transmitting and make sure that it's what it used to be before. Okay, so that was like a brief introduction to these three types of environments. Now let's talk about defenses in each of them and attacks and defenses in each of them. All right, so again, I'll start with industrial control systems. So here, the adversary model that we want to think about is an adversary that has access to this control network, and they have full access to it. They can inject any packets that they like. They can replay packets. They know the keys. They understand what the commands are. So there's no secrecy. There's no security by obscurity. We assume the attackers know exactly what's in the PLCs and what each command is supposed to do. And they're trying to manipulate the network to do something like create a water hammer, or do water hammers where you can open and close valves rapidly enough so that a pipe ruptures. So this is what the adversary wants to maybe do. And what we can do as defenders is deploy a network intrusion detection system, which can be either signature-based, or anomaly-based. So antiviruses use signatures, and they're very common, but they're problematic because they need to have a database of signatures, so you can only detect attacks that you know about. Any kind of unknown and novel threats, they're blind to. So the alternative is to use anomaly detection, basically model the normal traffic and then find any kind of anomalies that differ from what is supposed to happen and flag them as anomalies. And it's possible to do that. And we think it's important to also model not just the messages themselves, but also their order, the sequence of messages, and the timing of the messages. So these are other pieces of information that can be used. The challenge here is to avoid high numbers of false positives, okay? Because a system that complains every second is a system that the control room operator is going to shut down or ignore because it's bothering him too much. Okay, so one of the first things that we did probably 11 years ago is we made the following observation. We said, okay, industrial control networks are typically very static. The topology doesn't change because you have the machines and they're connected to their PLCs and they do what they do. And it's not like a home network that people, your guests come in and connect with their phones to your home network. It just doesn't happen. A turbine is a turbine. It has a PLC. That PLC is there for many years and it has the same address and it's doing the same thing. And also the traffic itself, so you have a PLC talking to something else, that is very, very regular. The pattern of communication is very repetitive. It's not like people browsing the internet and clicking on things. This is one machine talking to another machine, doing very, very specific things. So we thought that we could model this type of traffic using a very, very simple model. And we picked probably the simplest thing we could imagine, which is the deterministic finite state automaton, or a DFA, which you probably, I don't have to explain to you what that is, but basically it has a state, and on every type of message that it sees, it transitions to another state, and so on and so forth. You'll see an example in a second. So basically in the learning phase, we record the traffic and build a DFA from the observations. And then in the enforcement phase, we do the same thing for every message that is sent on the network. We do the appropriate transition and see if we find any kind of anomaly. If something is irregular, then we raise an alert. And here's an example of what kind of DFAs we use. So the basics of the DFA is the black arrows in the middle here. You can see that it has 4 states in this example. Each arrow represents a message. So you can see that there's Q messages and R messages, where Q means query and R means response. So when we are in the first state, that indicates that we got a query, then we see a response, and then we expect to see another query, and then we expect to see another response, and then we need to see another query of the type, the first one, and we basically have here a loop of normal traffic patterns that says query, response, 2 queries, and their 2 responses, and this goes on forever. Okay. Basically imagine saying, okay, what's the temperature that you're reading? You get an answer, and then it says, and what's the pressure that you're reading right now? And it says what the pressure is, and then this goes on forever. Okay, so these are this is a normal loop. These are the black arrows. All the other arrows are various types of anomalies. So the blue arrows indicate a message that was retransmitted. The yellow arrows indicate a miss. So we expected to see a black arrow with a query, and we didn't. We just saw the response, so we missed something. And then we have the red arrows, which are unknown transitions. Okay, we expected to see response number 1. Instead, we see some other kind of message that wasn't in the normal model, so it's unusual. This is an anomaly. Okay, very, very simple traffic model. And then we tested this. So this is something that I'd like to share with you. Getting data is really important and sometimes really, really difficult. Getting industrial control networks data for real is a big problem. It took a long time for us to get some of this. And the first network that we actually had access to was right under our noses. We just had to talk to the right people. So we found out that the housekeeping, the facilities management on our campus were running an industrial control system. We, as researchers, we didn't know that, but you talk to these people and say, oh yeah, we do that. What do you do? Well, we have a system that monitors electricity consumption in the buildings on campus. And one of the staff has a computer in his basement, and he looks at it and he can see how many kilowatts the campus is using, and how are the switches up or down in the buildings and so on. And they were kind enough to let us record this traffic for a few days. So we recorded them, and this is some of them from the statistics of what we got, and then we were able to experiment. So if you're interested and you want to do this kind of research, go find a network nearby, a friendly network, and get access to it. And you might be surprised. I mean, the air conditioning system in your building might produce this kind of traffic, and many others are like that. So getting data is really crucial if you want to do any kind of research in this area. Okay, so we took that and we analyzed it using the DFAs that I showed you before. And these are graphs showing how many unknown transitions happened over time. I think every tick on the x-axis is 15 minutes. And the y-axis is how many unknown transitions happened in that tick. And you can see that almost all the time there's nothing. Okay, the model and the actual traffic are perfectly synchronized, no anomalies, everything is exactly right. But we do see these spikes, especially over here around the 450 the frame index, which was weird. We looked at this and we thought we had a bug. So we went to talk to the engineer and said, okay, what happened on this and this date at these hours? We see some really weird network traffic. What's going on? Do you remember what happened? And he did. He actually said, oh, yeah, that day I remember that, because we had a technician walking around and we had some problems, and he was resetting things, and he was doing deploying things. He was doing unusual things. And this very simple model caught it. Basically, these spikes are true anomalies that were detected by the model. The anomalies were not malicious. They were benign, but still they were definitely anomalous. So it worked. So if you want an interim conclusion, anomaly detection can be made to work on industrial control systems. And even with very, very simple models like state machines, they can be very effective. And because they're so simple, they can work with trivial memory amounts, and they work in line speed, and they are extremely efficient. So this was a very happy result for us. I was surprised that it worked so well. The challenges, of course, are the false alarm rate, and in particular, and this is something that we always need to be aware of, mean time between alerts. It's not just the rate. Okay, saying that the system has 0.5% of false alarms may be good, may be completely unacceptable, because it depends on how many packets per second are sent. If you have 0.5% of false alarms, but you have 1,000,000 packets per second, then the red light is going to blink all the time, and the operator is going to turn it off. Okay, Roland is asking if you install patches, do you still have a static system? So yes and no. The system, the topology of the system is static, so you typically are not adding new PLCs, but potentially, so that's the yes, but the no is if you're installing patches, maybe the pattern of communication might change because the new system might be different. Although when you install patches, typically you're installing patches to the operating system of the PLC. What causes messages to be sent is not the operating system, it's the control logic. And the control logic is not a patch. Control logic is what the process engineer decided, how to implement their differential equations. And that part pretty much remains stable. But it's a good point. So let's continue. Let's talk about Siemens for a little bit. I showed you the experiments that we did were on Modbus. Let's take a look at Siemens. Much more, I'm going to show you stuff that we did 2 years ago with some other colleagues. And this was the work that we showed in Black Hat 2 years ago. So like I said before, the most famous cyber attack on industrial control systems was Stuxnet. And Stuxnet actually attacked Siemens protocols, the S7-300 PLCs. What's on the left here is called the TIA. That's basically the user interface. It runs on a PC. And here's the PLC on the right, what the Stuxnet did was it infected a particular DLL that is in charge of communication with the PLC and running the S7 protocol. So between the PLC and the Windows machine, there's communication using the proprietary S7 protocol. And what Stuxnet did was send commands to the PLC to do bad things while telling the TIA that everything was cool. Okay, so Siemens listened. They didn't like the fact that their PLCs were the target of this attack, and they improved. And so now their latest product lines. Now they have the S7 1500. This is the latest series of PLCs. This is the latest, the high-end model. They also have the S7 1200 series. There's multiple models here. And from my point of view, the biggest thing that they changed here is they actually changed the protocol. Okay, they added to the S7 protocol, which used to be completely insecure and defenseless, they added integrity protection. Basically, in S7 on the 1500 series, all the messages are cryptographically signed. So somebody malicious, even with access to the network, cannot send or should not be able to send legitimate packets that will convince the PLC to do anything because the signature is not going to be valid. That's the idea. So Siemens, since they have a monolithic system and they can make changes, they did so, and they improved the security of their system for their customers. And they can do this because it's a proprietary protocol. It's a walled garden, so they can do whatever they like. They can unilaterally upgrade the protocol without getting any kind of standard bodies approval or any kind of business partner approval. They can do whatever they like, which they did, and they made things better. But since it's proprietary and non-standard and not open to peer review, it's difficult to know what they did because they don't, the marketing material doesn't tell you what they actually did. So it's interesting to do reverse engineering and to actually understand what they truly did beyond the marketing stuff. And sometimes we find surprising things. And I'll show you an example right now. So as I said, the messages are cryptographically signed. So how is that done? Well, there's, first of all, the PLC and whoever's talking to it, the PC, need to agree on keys. Okay, so they run this little protocol where the PLC has a public key and its private key, and the client has the public key of the PLC. So there's a public key infrastructure where the PLC has the PLC has the secrets, and the clients have the public key. And then there's a protocol. The client says, hello, I want to talk to you. And then the PLC picks a random challenge and sends it back. Then the client randomizes something else, which is called the KDK, the key derivation key, creates keying material from this KDK and encrypts it using the public key of the PLC and sends it back. The PLC then decrypts this keying material with its private key, checks it likes what's inside there, and assuming that it's acceptable, it says, okay, fine. And then both of them have the same information, both the challenge and the keying material. And from this, they compute a session key using some kind of one-way function from these two inputs. And every message beyond this handshake is going to be signed using a message authentication key with this session key. So far, so good, and very similar to stuff that we know about. But here's an analogy to the equivalent thing that happens between browsers and websites. So using Tls Ssl, same type of situation. The server is analogous to the PLC, and the client, this would be a browser here. This is, let's say, the TIA system. But the twist is that in Tls Ssl, every server has a different public key, right? Every server on the planet generates its own private key, public key pair and publishes the public key. With S7, what we discovered is that actually Siemens, the company, produces these public-private key pairs in their factory, and all the PLCs from the same model and the same software version use the same key, same private key, same public key. Okay, so this is kind of not so great, because if the bad guys can extract the keys from one PLC, then they can attack every other PLC on the planet. And in fact, you could buy a PLC from the model that you care about, take it apart in your lab, extract whatever you can from it, and now you can go and attack the targets that you really want to attack. So we thought that this could be done better. Then we also looked into how all of this works. So how do they do all this crypto magic? And we actually were able to write an attack script that does all of this crypto and pretends to be or impersonates the TIA. So it can actually program the PLCs. So and what we did was we actually showed how you can mix and match. You can take two programs, let's say the yellow program and the blue program, and download something into the PLC which is half yellow, half blue. So you can cut and paste pieces from here, pieces from there. Neither of these, these pieces don't fit together, but since we can replace the four-way handshake, our code can talk to the PLC, convince it that everything is cool, and sign messages with integrity protection, and convince the PLC to do what we want. So we can actually replace the control logic on the PLC to do whatever we want it to do. Anyway, we put up a demo. You can search my webpage. You can see a link to the demo. We can actually demonstrate how all of this works. I'm going to zip forward here because we're running out of time. I want to show you a bit about the what's happening inside the crypto. Bear with me. There are some technical details here. If it's too much for you to comprehend in the 5 minutes I'm going to spend on this, never mind. I'll come back to more simple things after that. But just to give you a taste of what's going on. So this was the beginning of the protocol that I showed you, right? There's a challenge that the PLC picks, and there's the KDK that the client picks. And then once they have these two red pieces, they're going to eventually compute the session key using some kind of magic function F. Lovely. But what is this keying material? How does the client take this key derivation key and send it? It doesn't send it in a very obvious way. So what does it actually do? So once we looked into it, we found that it's doing a lot of things. There's all of the things on this screen stuck in there somewhere. There is a public-private key between the private key on the PLC, the public key on the client, that uses an elliptic curve El-Gamal type of system. And inside of this, there's also AES. There's two flavors of AES there, both ECB mode and counter mode. And it's also using some kind of custom key derivation function, and also uses some kind of non-cryptographic checksum, which is a tabulation hash. It's really complex, surprisingly so. This is what it looks like. So we actually reverse engineered the code and came up with this super simplified diagram. It's accurate, but it's took a lot of work to figure out what all the pieces were. Where I'm not going to go over them. Just imagine that there are lots of these different pieces. And what we came up with was that actually, if we want to cheat, so we're playing the part of the client, we don't even have to pick any kind of randomness. We can just decide that we're always going to use the randomly chosen key, all zeros. Pre-calculate everything that's shaded. All these bits are only dependent on this pre-key. So we can compute all of them once and for all in advance, then wait for the challenge to come in, and then on the fly do the rest. So they do this AES encryption and then feed the tabulation hash and do the key derivation, yada, yada, yada. We get all this keying material correctly, send it to the PLC. The PLC will use it and be happy. And we use this to do our reprogramming without the TIA. And of course, we told Siemens about this, and they patched the system, and so responsible disclosure and all that. And we talked to them, and they actually said, regarding our first point, that they're using the same key for all PLCs. They said, "Oh, but this is on purpose. We did this by design. This is how we want it to be because they have reasons." Which you can agree or not agree to. And what we thought that, well, okay, it's probably can be done in a better way. This is a very unusual mix of crypto components that Siemens invented. I mean, they used components that are standard, but they put them together in unusual ways. And we think it's better to use something standardized, like why not just use SSL like everybody else? And maybe they are. I think I heard rumors that they're switching, but don't quote me on this. Okay, so this is that. Okay, I promised to talk about CAN. So this is something completely different. Forget about industrial controls, come back to thinking about cars. So cars run CAN bus, and like I told you before about this broadcast message, I want a few more details here. So each CAN message has a message ID, 11 bits, saying this is message number so-and-so, and then somewhere in the data it says, the 64 bits of whatever it is that you want to transmit. Okay, CAN bus is prioritized based on the message ID. So message IDs that have lower numbers have higher priority. And in fact, it's not just that, there's prioritization at the bit level. So CAN is a slot based, so every slot, there's a time slot for a single bit, and multiple ECUs can transmit during the same time slot, and the bit that actually wins is the 0. The 0 is dominant. If there, 2 zeros are transmitted or 2 ones are transmitted, then nobody notices because they're the same. But if one ECU transmits a 0 and one ECU transmits a 1, there's a collision and the 0 wins. Okay, the 0 wins and the 1 loses. And notices, it's possible to notice this. And if that happens, then there's the standard calls for sending out an error flag indicating that there was a collision error, and the transmitting and receiving systems count how many collisions occurred. If there are too many collisions, then they sense that something is wrong. So they count. They have 2 counters. They're called the TEC and the REC. So this is the transmission error counter and receiving error counter, and they count how many errors. Each ECU counts for itself how many errors it encountered. Usually they're in what's called error active mode, so they're just working as usual. But once the counters reach 128, then they switch into what's called error passive mode, which means that if I encounter the error, I'm not allowed to broadcast any kind of flag telling everybody else that I've seen a collision. I have to be, if I'm seeing so many errors that maybe I'm malfunctioning, then I need to shut up. So error passive is sort of an intermediate state. And if the counter, the TEC or the REC reaches 256, then the ECU goes in what's called bus off. It actually disconnects itself from the bus, stops functioning until at a minimum you turn off the car and restart, or maybe you need to go to the garage. So getting to bus off means that the ECU shuts down, basically. So what's the adversary model? We said compromised ECU can send a fake message and cause actions to happen. And we wanted to create some kind of defense mechanism, an active defense mechanism that is not an anomaly detection. It's actually intrusion prevention or anomaly prevention. We wanted to actually block the spoofing. And to do that, we propose to do the following thing. First of all, we detect that a spoofing has happened. And we can do this because the detection unit is the legitimate ECU that is supposed to, that owns that message ID. If the ABS unit sees a message broadcast that it did not send, but it's using its own message ID, then it knows for sure that that's an attack. So that's the mechanism for detecting an attack. And then as a counter attack, what we do is we launch a counter attack. We send lots of messages that intentionally cause collisions with the adversary. And our goal is to drive the attacker into bus off. So we cause so many collisions so that the attacker shuts down. And we just need to be careful that we don't shut ourselves down in the process, because we also see collisions. So like I said, we identify the spoof by duplicating our own message ID, and then we start sending mass messages very rapidly in our counter attack. And the idea is to send messages that have lots of zeros in them. So either duplicate the message ID and exact the message length and just supply 64 bits of zero data. So this is the most dominant message you can imagine. Or we even send a message with a zero length. So zero length means that there's, in the length field, there's zeros, and the length field is earlier in, here's this DLC is the length field. So you put the zeros here rather than here, causing lots of collisions. And by doing this, and being clever about it, we drive the attacker to bus off and not shut ourselves down. This is what it looks like in a scope that tracks the bus. So at the top, this is the attacker messages. You can see that in our example, they're transmitting some, FFF, some kind of a message, and these are the messages that that Alice, the defender, is sending with lots of zeros, and believe me, this is a collision, and then there's an error and so on. And what happens is that once you create a collision, the CAN controller, the hardware, automatically does a retransmission. It immediately sends the message again on both sides. So you're going to get immediately another collision, what we call a snowball effect. One collision immediately causes another and another. You get 16 collisions in a row, and then both sides get into error passive mode. They cross the 128th threshold, and then they go into error passive mode. And then we force the 17th collision, which is silent. They're both in error passive mode. And this is, believe it or not, a tiebreaker, because we engineer it so that the defender system successfully completes the retransmission, and the attacker doesn't. The attacker does not complete. So we break the symmetry, and then we cause the attacker to have a few more collisions and go into bus off. And believe it or not, this works. This is a screenshot showing that we could do this. And if you want some of my thoughts here, that if you dig into obscure corners of the standard like this, these counter features that were designed for something completely different, sometimes you can find interesting features and repurpose them for defensive goals. And if you do that, you're lucky you can do these things and move forward. Now I'm running out of time, so I'm going to zip through the anomaly detection that we did for ARINC. There's very interesting things that we did there. This was in ESORICS of last year. If you're interested, you can go and check out the paper. I'm going to skip all this and just there share some final thoughts with you, which are that retrofitting security into legacy networks is, first of all, important, because these are important systems to secure. It's also interesting, at least I find it interesting. So I hope you did too. There's much more that you can do than you would think informally, even though the systems are old and they're not really evolving and they're very rigid and you have all these rules to work with. You can do a lot more than you imagine, but it does require some ingenuity. You need to find ways, find clever ways to inject the things that you want into these old systems, which is cool. I mean, we're in research, so interesting things and ingenuity is what we're here for. So with that, I will conclude and hand it over to Georg to wrap up. If you have questions, you can still ask me over the chat. So thank you for attending, and Georg, the floor is yours.
Thank you very much. Are there any questions right now in the audience? Is there anything you would like to know about more details? This is the moment. I just have one final question. Where do you see the biggest installations like power plants or dams holding water in a whole valley where a little stitch by a shrewd attacker can cause the most damage to people?
Well, it's hard to imagine right now, but well, we've seen that power plants and water treatment facilities and also oil and gas pumping and pipes, all these critical infrastructure type of things are full of these industrial control networks. They're full of PLCs, and they're prime targets with potential significant damage to populations around them. Water treatment, sewage treatment, same type of things. A lot of damage could be caused. And we've seen cyber attacks, cyber warfare attacks against these kind of critical infrastructures. This is already happening. Armies in the world are doing it. So this is not just pipe dreams. Sorry, excuse my pun. We have yet to see a wide-scale attack against cars. All the attacks that we've seen in the wild so far have been basically by good guys showing that the system is vulnerable, and not by actual adversaries trying to cause damage, even though they can. But time will tell. I mean, if criminals realize that it's simpler to steal cars using cyber attacks than it is by breaking a car window and or towing it away, then they'll do so. So in the car industry, I think criminal activity is kind of a big threat. Maybe it will appear before cyber, national cyber warfare. That's a speculation on my part, but I think that national warfare will attack national infrastructure, whereas attacking vehicles is more of a criminal activity based on generating profit. And airplanes, well, maybe terrorists. I don't know.
Where do you believe is the loophole? Are there engineers who don't have the know-how? Is there managements that don't understand the threat and just don't take the decision to buy what it takes to improve the legacy systems? Or is it politicians who have no clue to take the decisions and call for the improvements in public installations?
Probably number two and number three. I think that it's lots of these activities are private. Okay, so car manufacturers, car operators, aircraft designers, industrial control system users, power plants, water systems, all these are private facilities. The companies, they're profit driven. So for them, these threats are an externality, right? What's in it for a power plant to invest millions of dollars in upgrading their network? It's working for 40 years. Why invest now? So my expectation is that corporations are not going to do the necessary work on their own. When they need to build a new power station, they'll buy the latest from Siemens, but replacing the old, it's working. They're not going to replace the old unless somebody forces them. And regulators are flexing their muscles a little bit. They're not being aggressive. Politicians and regulators are very much friends of the industries that they regulate. So they are very hesitant to force them to spend lots of money. And they certainly are hesitant on saying, okay, we'll spend the money for you. The government will pay for upgrading the systems. So, and also some of the threats are intangible. So people don't have imagination. If I tell you, your car is vulnerable, you'll probably say, yeah, okay, I have bigger threats that I'm worried about right now.
Like the beer I just had before driving.
Yes, there's, everybody's, and it's not just individuals, corporations and companies and governments all have priorities. And well, is it real? I don't know. Stuxnet proved 11 years ago to governments worldwide that this is very real and it can be used against them. If the Iranians were attacked, why not us? And so they started paying attention, and Siemens started paying attention and paying money, and things are happening. For cars, it's somewhere in the middle. Cars are more, we haven't seen an attack. So, it's not that, but car manufacturers are moving in this direction. There's a whole cyber industry of securing cars. There's a whole conference called SCAR that's devoted to that. There's lots of startups. All the big manufacturers are doing things to secure their cars in many ways, especially as they're introducing more and more connectivity to them. So they're doing the right things. With aircraft, to the best of my knowledge, a lot of it is still security by obscurity. The aircraft industry is not embracing making radical changes yet. Governments are not forcing them. It's basically two manufacturers, right? There's Airbus and Boeing and some smaller ones. And maybe they're changing things, but it's not a big industry as far as I know. My sad prediction is that they're not going to do much until aircraft start falling out of the sky. So once we see an actual plane crash somewhere due to a cyber attack, that somebody took over an airborne system somehow and caused the plane to crash and people die, then politicians and manufacturers will notice. Before that, who knows? I'm not optimistic.
Okay. Thank you very much, Professor Avishai Wool, for your insight into this crucial research. Thank you in the audience for participating. The next tutorial will be in 2 weeks on August 24th. Professor Dr. Juraj Somorovsky from Paderborn University, Germany, will talk about transport layer security. He'll show how you can analyze TLS 1.3 with Wireshark and TLS Attacker. Come join us then again in 2 weeks. Next week, we will have the registration page live, and you will be welcome to register for the ESORICS conference from October 4th to October 8th. See you.